Semiconductor chips are the invisible engines that power nearly every modern device, from smartphones and computers to automobiles, satellites, and even household appliances. These tiny pieces of silicon, often no larger than a fingernail, contain billions of microscopic transistors that process information and control electronic functions. Without them, today's digital world simply wouldn't exist. The process of making these chips, however, is anything but simple. It combines physics, chemistry, and precision engineering at the atomic level. Creating a single chip can take several months and involve hundreds of highly controlled steps inside ultra-clean environments known as fabs, fabrication plants. Each step must be executed with incredible accuracy. Just a few atoms of error can render an entire batch unusable. In this article, we'll explore how chips are made, starting from raw materials like sand, through complex manufacturing stages such as photolithography and etching, all the way to final testing and packaging. By understanding this intricate journey, we gain a deeper appreciation for the technology that fuels our connected world. What are semiconductor chips? Semiconductor chips, also known as microchips or integrated circuits, ICs, are tiny electronic components that serve as the foundation of nearly all modern electronic devices. They are made from semiconductor materials, most commonly silicon, which has electrical properties that fall between conductors and insulators. This unique characteristic allows engineers to precisely control the flow of electricity, enabling chips to perform complex operations. Inside each chip are millions or even billions of transistors, which act as microscopic switches that turn electrical signals on and off. These transistors are arranged in intricate patterns to create circuits capable of processing data, storing information, and managing power. There are several types of semiconductor chips, including logic chips, used in processors and AI units, memory chips, for data storage, and analog or power management chips, for signal and energy control. Although small in size, semiconductor chips are incredibly powerful. They function as the brains of modern technology, processing information, enabling communication, and driving innovation in everything from smartphones and computers to medical devices, cars, and satellites. Raw material. From sand to silicon. The journey of making semiconductor chips begins with one of the most common materials on Earth, sand. The primary element used in chip production is silicon, which is found abundantly in quartz sand. However, the silicon used for semiconductors must be extremely pure, far beyond what is found in nature. To achieve this, the sand is refined through a chemical process to produce electronic-grade silicon with a purity of more than 99.9999%. Once purified, the silicon is melted and grown into a large single-crystal ingot, using a method called the Czochralski process. This process involves dipping a small seed crystal into molten silicon and slowly pulling it upward while rotating it, forming a perfect cylindrical crystal structure. The resulting ingot, often weighing hundreds of kilograms, is then sliced into thin wafers, each just fractions of a millimeter thick. These wafers serve as the foundation for semiconductor devices. Before they can be used in chip fabrication, the wafers are polished to a mirror-like finish to eliminate any surface defects. The result is a flawless, ultra-flat silicon disc ready to enter the cleanroom environment, where intricate patterns of transistors and circuits will be built upon it, layer by layer. From something as simple as sand, the transformation into a high-tech silicon wafer marks the first step in the fascinating process of how chips are made. Wafer fabrication process. The wafer fabrication process is the heart of semiconductor manufacturing, where the silicon wafer is transformed into a complex network of transistors and circuits that make up a microchip. This process takes place inside a highly controlled cleanroom environment, where even a single dust particle can ruin an entire wafer. The fabrication involves hundreds of precise steps, repeated multiple times to build multiple layers of circuitry on the wafer surface. The process begins with oxidation, where a thin layer of silicon dioxide is grown on the wafer to act as an insulator. Next comes photolithography, one of the most critical steps. In this stage, a light-sensitive chemical called photoresist is applied to the wafer, and ultraviolet, UV light, is projected through a mask containing the desired circuit pattern. The exposed areas are developed, transferring the intricate design onto the wafer surface. Following this, the wafer undergoes etching, which removes the unwanted material to create microscopic patterns. Two main methods are used: wet etching, which uses chemical solutions, and dry etching, which employs plasma gases for more precise control. After etching, the wafer moves to ion implantation, also called doping, where high-energy ions are fired into specific regions of the silicon to alter its electrical properties, forming N-type and P-type regions essential for transistor operation. Next, in the deposition phase, layers of materials such as metals, insulators, or polysilicon are added to build the transistor structure. Methods like chemical vapor deposition, CVD, physical vapor deposition, PVD, or atomic layer deposition, ALD, are used depending on the material requirements. To ensure the wafer surface remains smooth for the next layers, chemical mechanical polishing, CMP, is applied, creating a perfectly flat surface. These steps, oxidation, photolithography, etching, doping, deposition, and polishing, are repeated hundreds of times to build the multiple transistor layers and interconnections that form a complete integrated circuit. Each repetition adds more detail and complexity, bringing the wafer closer to becoming a functional semiconductor chip. The wafer fabrication process is a masterpiece of precision engineering, combining advanced chemistry, physics, and automation to create the core of modern electronic technology. Circuit formation and integration. Once the wafer has gone through multiple cycles of photolithography, etching, and doping, it's time to form the circuits and integrate all the components that make the chip functional. This stage is known as circuit formation and integration, where billions of transistors are connected together through ultra-fine metallic pathways called interconnects. These interconnect layers allow electrical signals to travel between transistors, logic gates, and memory cells, enabling the chip to perform computations and store data. To build these connections, manufacturers deposit very thin layers of conductive materials such as copper or tungsten over the wafer. Using photolithography and etching again, these layers are patterned into microscopic lines, some just a few nanometers wide, that form the wiring network. Between each metal layer, dielectric materials are added to insulate the circuits and prevent short circuits. As technology advances, chips now contain more than a dozen interconnect layers stacked vertically, allowing for faster communication and higher transistor density. After wiring, the wafer undergoes planarization and cleaning to ensure surface smoothness and prevent signal interference. At this stage, the chip's logic blocks, memory regions, and input-output connections are all integrated into a unified architecture. Every transistor and interconnect must function perfectly together for the chip to work as designed. The process of circuit formation and integration represents one of the most critical and complex parts of semiconductor manufacturing. It transforms an ordinary silicon wafer into a highly intelligent electronic brain, capable of processing billions of operations per second and forming the foundation of today's digital technology. Wafer testing and inspection. After the circuits are formed, each wafer undergoes a series of testing and inspection steps to ensure that every chip meets the required performance and quality standards. This stage is essential because even a microscopic defect, such as a dust particle, contamination, or slight pattern misalignment, can cause a chip to fail. Since wafer fabrication involves hundreds of precise processes, Inspection is performed continuously throughout production to catch problems early and maintain a high yield rate. The first step involves optical inspection, where advanced microscopes and automated vision systems scan the wafer surface for scratches, cracks, or pattern defects. These systems can detect flaws far smaller than the width of a human hair. Next, electrical testing, often called wafer probing, is performed. Tiny probe needles contact each chip's surface pads to measure electrical properties like voltage, current, and signal response. This helps identify which chips function correctly and which are defective. Engineers then analyze the test data to calculate the yield, or the percentage of working chips per wafer. A higher yield means more usable chips, which is critical because manufacturing costs are extremely high. Defective chips are marked or mapped so they can be discarded later during the dicing process. In addition to visual and electrical tests, metrology tools are used to measure dimensions, film thickness, and layer alignment with atomic-level precision. This ensures every part of the wafer meets strict design specifications. Some manufacturers also use scanning electron microscopes, SEM, and X-ray inspection for deeper structural analysis. Through these comprehensive testing and inspection steps, only the wafers that meet rigorous performance and reliability standards move forward to the next stage, dicing and packaging. This ensures that every chip reaching the market operates with the precision and reliability demanded by today's advanced electronic systems. Wafer dicing and packaging. After packaging, the semiconductor chips undergo final testing and quality assurance to confirm that they meet all performance, reliability, and safety standards before shipping to customers. This stage ensures that only the best, fully functional chips reach the market. Even after extensive wafer-level tests, it is essential to perform final testing at the package level, since the assembly and bonding processes can introduce new defects or performance variations. The process begins with functional testing, where each chip is powered on and its electrical behavior is evaluated. Specialized testers run the chip through a series of operations to verify that it performs as designed, checking parameters like logic accuracy, memory integrity, and signal response. The chips are then subjected to parametric testing, which measures characteristics such as current leakage, power consumption, and switching speed to ensure they remain within acceptable limits. Next, the chips undergo stress and reliability testing. This includes burn-in testing, where chips are operated at elevated temperatures and voltages for several hours or days to detect early failures. Other tests, such as thermal cycling, vibration, and humidity exposure, simulate harsh real-world conditions to confirm the product's durability. Once testing is complete, chips are categorized through a process called binning, which sorts them by performance level. For example, faster or more power-efficient chips may be used in high-end products, while lower-performance ones are used in budget devices. Finally, every batch undergoes quality assurance inspections following international standards such as ISO and JEDEC. Only the chips that pass all functional, electrical, and environmental tests are approved for shipment. Through this rigorous final testing and quality assurance process, manufacturers guarantee that each semiconductor chip operates with the precision, reliability, and stability demanded by modern technology. The creation of semiconductor chips is one of the most complex and precise manufacturing processes ever developed by humankind. What begins as ordinary sand undergoes an extraordinary transformation. Through purification, crystal growth, wafer fabrication, circuit formation, testing, and packaging, into a tiny yet incredibly powerful component that drives today's technology. Each stage requires advanced machinery, nanometer-scale precision, and cleanroom environments where even a single dust particle can mean failure. From powering smartphones and computers to controlling cars, spacecraft, and medical devices, semiconductor chips have become the heartbeat of the digital world. Their development reflects decades of innovation in materials science, physics, and engineering. As technology continues to advance, chip manufacturing will evolve toward even smaller, faster, and more efficient designs, enabling breakthroughs in artificial intelligence, quantum computing, and beyond. In essence, the journey of how chips are made showcases human ingenuity at its finest, turning grains of sand into the intelligent circuits that shape our modern lives.